Okay, so after some Zoom issues, let's work again in our demonstration so I can demonstrate how this works. So basically, at this point, I have my file here, and basically this is the original file, right? And basically, if I run the ransomware here, what happens is that I still have my files, but this actual file was encrypted, right? So basically, I don't have the key to open it. It's a game over for me. I lost this file, right? Of course, this is a toy ransomware, so I didn't actually um, encrypted anything. I just used an XOR, right? So basically, this is the XOR version of the previous one, such that XOR is reversible. If I XOR this same thing, this same content with the same old key, the original content is back, right? But in a real ransomware, you don't have this option in general if the crypto is well implemented. So you lose, unless you have a backup, right? So you can have a backup like this, okay, and then my file is back, right? But let's suppose that you don't have a backup. Your file was encrypted. Is there a way to revert, to recover it? Well, if the implementation is not proper, not adequate, like having these type of flaws that we have been discussing, then yes, there might be something that's possible to do. So let's investigate this file a little bit. So as you can see, I have the source code of the file, but I will try to present it without showing you the actual source code of the file. Let's just inspect the file. So let's use GDB on the ransom uh, application. So let's go up to the main. We can run until there, right? We can disassemble, and then we can see more or less how this application works. We see some information like it closes file, which makes sense for a ransomware that operates on file. It reads directory, which also makes sense to enumerate the files in a directory. We have file put content. Basically, it's writing the content into the file. We can start to see that things make sense. And at some point, it's reading the file. It is open the file. All those things make sense for a ransomware, operates over strings, open directories, and at some point, get key. So this function is probably very important for the operation of the ransomware. So let's stop at the function get key. So we let it to run until the get key, and let's disassemble the get key function. That is a little bit longer, right? So basically, we can see what it does. So basically, we are going to find some rand calls here, as we can see. So it calls rand. If we see something more, we are going to see it calls rand again for the second time. It calls rand again for the third time. So this ransomware, just looking here, we see that it operates the way that I discussed in the slide. So basically, consecutive calls, each one's accumulating the values of the previous ones, and these values probably are seeded here, as you can see before the first rand. There is the srand, this rand seeded with the value of time, right? So basically, that's what it's doing. So if we stop at this location, right? This location, let me store what is the location. And then later you're going to store the value. So if we stop at this location, AX is going to have the value of the seed, right? So let's put a breakpoint in that location. We let the execution to go until there. And if we get the value of AX, this value here is the seed used by the operation. Let me store it here for a while. Okay, so this is the value of the seed. And then if we let it go, the ransomware is going to seed the rand with this function, generate function numbers. It's going to become the key, and it's going to encrypt. So we can let it run until the end, right? And okay, if we leave GDB, and then we check that all my files are still here, but if I get my file is now encrypted. But what's the point? The point is that now I got what were the keys. So I discovered somehow what was the seed, right? Because it was in the file or something like that. Let's assume that was the case. We have the key, so the seed. The seed is this value, and then we can go back to this location, right? And then see what's going on. So we can run the ransomware again, because if you remember, this is an XOR base. So if I run the ransomware again, it's going to XOR again with the same key, and XOR the old value with the same key is going to restore the content. So basically, I can run the ransomware again. I can go until the same location. I can leave it run until there, and at this point, I can check what the value of AAX. The value of AAX, notice, now I'm running after this old one. So the time has passed. So the time here that we have here is bigger than this one, right? As you can see here, it's bigger value, right? So basically, if I simply run these things, I'm not going to recover the key because the key that's going to be generated from this value is different, right? But what I can do is that I can set the value of the AX, the seed, to the previous value, right? And now in the register, I have my value. I have the same seed as before. And then I can let the execution to proceed. So it's going to generate the random numbers from this value, and it's going to encrypt. And if I do that, if I let it run until the end, when I leave GDB, I still have the same files, but when I look to the content of my file, the content was stored because I generate the same key, encrypted the same key, in this case an XOR, so recover the value, right? So this is how we can recover a key from a ransomware if it uses a weak implementation. Of course, this is a very toy case, but it's enough to demonstrate the viability. So right now, what you have to do in practice is that we have to do this for the assignment. So let me open the assignment here, and the assignment is basically redo what I did. I'm going to provide you with a toy ransomware, and all that you have to do is to repeat this process that I demonstrated, recover the key, and please let me know exactly what are the addresses, what are the keys, what are the seed values, and all those things, right? That's what we have for today. See you next class.